talk about is kind of setting up the idea of being able to do a state space. In order to kind of set up doing a state space, there's kind of a few background things we do. Essentially, the reason why I want to talk about state space is kind of the matrix description of our system, and then we'll use that matrix description to develop at least an initial understanding of modern control theory. That's kind of like the outline. Hopefully I'll get through enough of state space so that you can at least see where such a thing could come from today. And then my hope is to be able to use some of those results next time. So that's kind of that one. Now, to do this, I don't have a lot of time to develop a lot of the mathematical mechanisms behind here. So I'm going to try to make it approachable by showing you how some things work together. But that kind of means I have to backwards into this. So rather than kind of power through transform theory and the rest of this kinds of stuff as it goes on, and there are some ones where we can do this and do calculus and variation and stuff of this sort. I'm going to actually do this by taking a look at our actual transfer functions. We look at them from block diagrams. Okay, and then we're going to see how we can develop either a state space description from the block diagram or the modern control description from it. And once I've shown how you can get either from there, we can get to that point. So I'm going to start off with an assumption of block diagrams. And we're going to take a look at a particular form of a block diagram. Imagine for a sec that I had some variable, let me call it x3. Right? And so I'm going to put my labels on the axes as I've done in the past. And let's say that I have a series of these different ones that are connected by taking 1 over s as their transfer function. Now, what does that imply to you when you see the 1 over s?
In what time domain?
Yeah, well, I wasn't.
Integrated.
I've integrated. Okay. This is telling you a chain of integration. That's a fairly comfortable thing. I haven't told you where these particular states have come from, but you can see that, you know, for instance, x3 must be the derivative of x2. All right. And then what we'll do is we will take these, and these states I'm going to feed forward. Oops, I should call that x1. That's 1, 3, 2, 1. So now I haven't labeled anything there, so you can assume it's doing straight addition. Now, the other thing I'm going to do is I'm going to have a second summer at the beginning. I'll have some input coming in. And then I'll feed these back. Fair enough? Okay, now what I want to do is kind of figure out what is the transfer function of this whole thing. Fair enough? So to do that, we've got to do some block diagram algebra. Now, we kind of see this nice little feedback loop here that's going on. You know, and maybe I should, I'll put these as minuses just so we have negative feedback as it goes on. So I see this kind of feedback loop, but I'm pulling something out from the middle.
Yeah.
So it'd be nice if I could actually pull this inside.
Which you can.
Which I can, yeah. I mean, in order to do that, though, I've got to account for this one will no longer receive this feedback.
Right. And
so, you know, this line x3 at the moment is equal to u minus a2 x2 minus a1 x1. Right? That's what x3 is equal to. If I pull this one inside, that means until after that one happens, I don't really have x3.
Right.
I have something a little bit shy of x3, and what I'll be shy of is this term right here.
Wouldn't you be shy of both A2 and A1?
Right? No, I'm saying, what if I split this one? Because it would be nicest of all if I had x3 here. Imagine I just made two
Oh,
summers.
yeah.
Right? So that at this point I have x3. And if I were to take this right here, nothing's changed. I can split those up and just say, you know, this still says x3 is equal to u minus a1 x1 minus a2 x2. So this point is exactly the same, but I would like to pull this one out.
Right.
The second I pull this one out, it still has these two components, but it's missing this component. We agree?
Yep.
Which means I've got to add that back in. So in order to get that in, taking a look on here, I could consider it as if there was a second line when I pulled it off, which took this value here and fed it through a minus b and kind of added it in. If I did that, I'd still be fine, wouldn't I? Because then I would just be taking this, which is what's missing. I've got the minus here because the negative doesn't happen until that point.
Yeah. Okay.
Right. And then, so I would have, being added in, I'd still have u times b3 and minus a1 x1 times b3. And I would also have minus a2 x2 b3. Do we agree that's the same?
Mm-hmm.
Now, that means this I can split also. If I took it from here, still the same, isn't it?
Yeah.
Right? All I've done is I've pulled it to the other side, so I have to pull in the A2. Right? But that's exactly the same as just pulling this directly from here. But that means this one and this one are in parallel.
Right.
Do we agree? So why draw two parallel loops? Why not just stick that one in? Right? It's a little bit neater that I don't have this ugly line going through. That means I need a slightly bigger space here because now I have to add that term in, which is minus a2 b3. It's an ugly looking 3. That looks a bit better. And now I don't need this line anymore. Do we all agree?
Yeah. That was much better.
The whole point of this was I wanted to pull that out because this I can solve for.
Right.
Before, I didn't have any easy form for it. Because remember, we only had a couple basic block diagram algebra rules. So I've got to massage them into the rules and then I can substitute. Make sense?
Yeah.
All right. So how about this? How can I reduce this one now?
They're in parallel.
Well, this is a feedback loop. So that means whatever's inside here has to look like 1 over s, the top,
Over 1,
over
1 plus 1 over s times a2.
We agree?
Yeah.
But that's not pretty, is it? Got 1 over s's in it and stuff like that. So if I multiply by 1, I haven't changed anything, have I?
Nope.
So I multiply by a particular 1, s over s. Which just gives me 1 over s plus a2. Much nicer?
Yeah.
Quite a bit cleaner. So we just go, okay, that's nice. And this has to be exactly equivalent to this whole loop, but it's certainly a nicer expression than it. So I can remove all of this here. and replace it by that. So far, so good?
Mm-hmm.
All right. Now I'd like to be able to reduce some more. But in order to reduce some more, I still have some other problems, don't I? I see another one of these nice feedback loops. That'd be nice to get rid of. But in order to do that, I have to account for these two things that are getting picked off. So first, this one looks the most challenging, right? So I'm going to take this one and pull it out. That would be good, wouldn't it?
Yeah.
Well, what this means is this multiplies the input signal to give me this.
Right.
And that goes to two different places. So the distributive rule means if I take this, right, and multiply it here and here, I've done the same net thing.
Right.
We all agree? Another way of looking at that is if I pulled this off from over here, both sides would have to have the same function in between. Right? This point is now just x2 again. Right? I just got x2 in two places. I haven't changed anything. I run through the exact same thing. There's no way of telling whether you're on that line or that line. They're identical. But the added advantage is that line's no longer in the middle here. As a matter of fact, these two both come from this point and go to right there. Therefore, they are in parallel. I can just add them together, can't I? Because that's a summer on the end. There's add them. So I take this line and add it to that line.
Right, okay.
Good? All right. So that means I need a little more room. So that was a B3, I believe.
Mm-hmm.
And now I've got 1 over S plus A2 times this, which is B2 minus A2 B3. We agree? It's now all I did is I combined those two. You just do that by multiplying since we're in the S domain.
Right.
Right? And then I just added them. Good?
Good.
Okay. So now I've got that taken care of. I'd like to pull it out though.
Right.
If I could pull it out, that'd be even better, wouldn't it?
Just have to
So if I pull it out, what happens?
add x1, a1 to it.
Huh? So yeah, if I do that, this line is in essence still multiplying the u, but I still have a minus a1, x1 that has to get added in. Huh? Which is, if you want to think about it, another way you could do this is I could just put a little summer block here and just there.
Yeah.
Haven't changed a thing, have I?
Nope.
Because I still have u going through that and minus a1x1 going through that. Exactly what I had before. But now, this is a completely free block.
Right.
So what that means is this block is the equivalent of top line over 1 plus top times bottom. So I can reduce again. Oh, my top line is 1 over s plus a2 times a 1 over s. That's the top. And then the bottom is 1 plus a1 times top, which is 1 over s plus a2 times s. Fair enough? That's ugly looking though.
Multiply by the
S plus a2
1
times
over 1.
Yeah, you could do 1 over 1, which is s plus a2 times s. That's one way of thinking of it. The other way of thinking of it is this on top means 1 to the top and this to the bottom. It's another exact way of thinking of it.
Right.
I just mentioned it the other way because you might like it better that way. Right? Just remember what this means. This is the equivalent of taking 1 times, I can just pull that out. I can factor what is the numerator out. This is another trick of using 1. It's just a different way. Now I don't substitute for 1. I just remember that it is always 1 times the top, and I factor the top out. At which point it just means multiply through by the bottom. Either way you do it, it's exactly the same. So I don't care which way you think of it, but you might think of one as easier than the other. So whichever one works for you, it works for you. That's awesome. All right? So this clears this term out, but then I get this over here in place of the 1. Right? So that means this has to equal 1 over s plus a2 times s plus a1. All right? Still not the prettiest. We could write that as s squared plus a 2s plus a1.
Cool.
Fair? That, I think, is a fairly nice little expression. Certainly a heck of a lot nicer than what we have right here. And what a A2S. Good? At this point, it's all feed forward. There's no feedback, so these are easy. It's just weighted scalings of things. So if you want to think about it at this point, now I'm going to split this one. So I have the u times that lovely thing, and then I have this one coming back in. This is equivalent to, and I had an A, I think it was A0, is that correct? Or was that A1? That was A1, okay. So I had, should be minus A1 times that whole mess up there. B3 plus 1 over S plus A2. Fair? These two are now in parallel. So I can just add them in. At this point, it's probably just easier to draw a new one. So now I've got B1, a little smaller, B1 minus A1. I'm going to distribute through just to kind of clean this up a little. B3 minus A1 over S plus A2 times B2 plus A1, A2, 3 all over S plus A2. So provided I haven't done an algebraic mistake, this combines together to make this, and you distribute it out. And then up top, we've got another big ugly expression, B3 plus B2 over S plus A2 minus A2 B3 over S plus A2. There. Yeah.
But again, B3 looks like a B2.
Where?
The-
Oh, does it? Oh, no, sorry. I stuck it up. That's not fancy. That's good notation. I don't mind claiming I put things in sloppy areas. So, but we agree with the rest? Okay. So these are just, right? These two have to multiply each other. And then you just add that to this. Okay? So that's going to make a big ol' ugly expression. Right? Which I'm just going to, at the moment, just say is called star. Gives me my output, where my star is just equal to, now I can off the side, so I have to keep drawing in boxes.
Right.
B3 plus B2 over S plus A2 minus A2 B3 over S plus A2. And then that's the top. And I have plus 1 over S squared plus A2S plus A1 times this all B1 minus A1 B3 minus A1 B2 over S plus A2 plus A1 A2 B3 over S plus A2. All right? It's a big expression, I admit. All right? But we've got this whole gigantic thing that goes in. So far, so good? Mm-hmm. Okay, so now I want to kind of combine them together to get common terms top and bottom. So on this one, when we're going through, I need to get denominators that look similar as it happens. So I have to combine all the way through. So let's take a look at my worst case. I've got this one times this part, right?
Right. Which is just S.
What's that?
Which that S plus A2 is going to be the same at least.
Yeah. So. We agree that's the biggest denominator I have anywhere. So everything, now I just have to make sure whatever's up there, if it doesn't have it, I have to include those in so it became multiplied by 1.
Yeah.
So the top is now going to be the big part. So I've got a B3 times S squared plus A2S plus A1 times S plus A2 plus B2 times S squared plus A2S plus A1. Actually, let me just combine those two together, if that's okay. Because they both have the same denominator. Save myself a little bit of writing. B2 minus A2, B3. There, that's just these two terms.
Yeah.
Plus, now this one automatically has that on the denominators. They all have that from all the remaining terms do. So this one is only missing, actually these two are only missing the S plus A2 on the bottom, which means I've got a B1 minus A1 B3, and that has to be multiplied by S plus A2. And then this one has everything. So that minus we agree?
Yes.
All right. Now, when we're looking through all of these as it goes in, all right, we've got a pretty big expression for what's happening here. But I want you to notice a couple things. We've got some kind of standard roots here. If you notice, almost all the terms, with very rare exception, involve the S plus A2 term.
Yeah.
Okay? You know, and even when you get down to, you know, to all these, you're only really dealing with this one, which is B3, which was the original, just take the input and feed it forward.
Right.
As it's going on. And that's the direct feed of the input to the output. How does your control affect it? as it's going on. So that's not too surprising that that's not there, but almost everything else includes that term as it goes, which is kind of a neat little pattern as we see going on here. Now, this means these are the poles you're considering looking at. Remember, that's what determines the stability of your system. This top part, and you can reduce this if you really wanted to. My primary concern mainly just being in showing that I get these, which is where my transfer function poles are equal to. Okay? And I've got them. Okay? Now, this is equal to, if you think about this, these are the terms that had to do with the derivative of your states as you were going in, feeding back from the original system. So those ones are describing to you in some sense when you're dealing with it. Remember when we wrote the original equation? When we were dealing with derivatives, let's say like x double dot plus a2 x dot plus a1 equals something. All right? So imagine I just had that. What would I have as the Laplace transform of that?
Squared plus a2s plus a1.
All right? So I'd have, in essence, my x as it goes of s squared from here plus a2 times s plus a1. All right, where this is now
Cap.
the Laplace. And that's equal to some. Right? And then what happens is you now have whatever that is, whatever you were trying to figure out, ends up being plus a2s plus a1 with a big F on top. Okay? Mm-hmm. So if you think about what's going on here for a second, the way in which I get these ones right here had to directly have been from some type of equation that looks like that. We've gotten those before. We've shown you get them from spring mass systems, and you get them from resistor, inductor, capacitor systems, and so on and so forth, right? This is what we did with Lagrangians. You can generate these things all day long as it goes on. So, but in some sense, that's kind of the system that you gain as it goes on. The top part here is basically telling you kind of how you weight things to generate your output. This is the describing how the system, the mechanics of how it operates. And the top part is, in essence, taking little samples of those and saying how much of that is used to generate the whole system. But our real big key thing at this moment is to figure out what's going on with those. That make sense? Now, given that, I want to take the same exact system for a sec and show you what happens if I wrote it a slightly different way. Okay? What if instead of just kind of combining it together in some big ugly expression, and later on we might want to come back and we can show there's some neat things about the top too that goes on. But let's say imagine for a sec that we took that original, I destroyed the original one. So I believe the original one we had was x3 1 over s x2 1 over s x1, and I think I had b0. You will have to help me remember if I get something wrong here.
B1.
Both b1?
Yeah.
b1. And then we had all right. All right. Now, think about what's going on. X3, I could alternately just straight out write down what is the expression for X3. X3 is equal to minus A2 X2. Right? And I've got minus A1 X1 plus U. We agree? All I'm doing is saying x3 is equal to whatever comes out of this, which is just minus a2x2 minus a1x1 plus u. Good? So I can write that expression down. How about x2? What's the expression for x2?
1 over s times x3.
Huh? Yeah, so I had to integrate s3. Right? 1 over s times that. But I could also, that's integration, which is telling you that if I took the derivative of x2, that'd have to give you x3, right?
Yeah. Right.
And how about if I want to get an expression for x1? Well, I know x1 is the integral of x2, isn't it? Nothing else added in. So that means the derivative of x1 must be x2. Fair? So what if I considered for a sec, right? Because if you think about it, this is just x3. I could just substitute this in. And what I would then have is a nice little differential equation. x1 dot equals x2 dot equals minus a2 x2 minus a1 x1 plus u. Would agree? Write this as a matrix. x1, x2, I call that my vector. Take its derivative. It's got to be equal to something, x1, x2. You can see it's nice and linear. The top row, x1 dot, is just x2, which means none of the x1s and one of the x2s. Agree? x2 dot is minus a2 x2 and minus a1 times x1 plus I need to add in a u term down here, but I didn't need to do it up top. We agree?
Yeah.
So that describes how I can get my x's. But I still haven't said how to get y yet.
Right.
Now, if you watch, y, my output, that's equal to x1 times b1, x2 times b2, and x3 times b3. So, if I take the same situation with my x1s and so on, right? So I can take my x1, x2, x3 as we go on, and I can take those and say, great, take them in, and now I can just take those and go that's b1, b2, b3, as going in for these. But I already know what x3 also is in terms of the other two, don't I?
Yeah.
I mean, x3 is equal to these. Now, why don't I just like this one as it stands? Yeah, it's not the same dimensions. But I can note that x3 is exactly the same as minus a2, x2, minus a1, x1, big enough, plus u. Agree? Which means that in essence this multiplies b3. So this expression is just equal to, I've got b1 x1 plus b2 x2 plus b3 times this mess. Just let me write that b3 first. agree? Then if we take these and combine together the terms that have x2 and x1, you'll notice that you end up with, again, a nice little equation. I've got b1 minus a1 b3. That's times x1. Multiplying x2 is b2. And then minus a2 b3. And then I have this extra b3 times u. Now it's the same dimension. We agree?
Yeah.
Now, this has some nice properties to it. Some properties that are actually amazingly similar. But do we agree that this describes the system?
Yeah.
Let me ask you, which was it easier to get? This and this, or that mess?
That.
This was a hell of a lot easier, wasn't it?
Yeah.
Okay? Now imagine when this scales to more and more feedback loops.
Right.
Which it goes more and more poles. More feedback, each feedback loop is giving me a pole, right? So imagine as this grows, I just did, what, 2 feedback loops? Now, notice 2 feedback loops, and what's the dimension of my system?
2.
It's a 2 by 2, which means size 2. 2 states. Each feedback loop gives you a state. This should not surprise you. Everybody's had digital logic, right? We got these things we called states, right? Inside of digital logic, your 310 course.
Mm-hmm.
And when you did feedback, if you fed back the output of something, like say I took a NAND gate or something, and I fed it back into itself, I could get memory, couldn't I? And that memory we called the state of the system. It's not an accident. Every feedback loop gives you state. It's no different here than it is there. This is a discrete system, that's a continuous system. That's the only difference. That is how you get memory. Memory is feedback. It's exactly how it is formed. It does not matter what course you take it. So believe it or not, when you are studying your control system stuff, you are studying 310. Okay? 310 just had some nice pre-chewed up results for you. That we usually started out by saying, consider the following thing. We make this table, you get this solution. How did we really know those worked? You can actually prove them. You can actually take, and there's a transform equivalent of the Laplace transform called the Z transform. You can take the Z transform of those equations that we got for the system when you start writing your state diagrams, and you will get expressions like this, and you can actually check to see whether it's stable or not, and how the transitions work and everything else. It's no different. Believe it or not, this is no different than what you learned a year or 2 ago. This is just being done in a much more general sense. And I'm proving it a little more rigorously this time. But it is really the same thing. So your intuition should carry through. Every time I have a feedback, I have a state. 2 feedback loops, 2 states. If I had 3 feedback loops, I'd have 3 states. Okay? So, and we already showed that every one of those feedback loops gave you a pole. So therefore, there should be a pole for every one of these states.
Oh.
Well, so far, so good?
Yeah.
Now notice, this is of the form, let me just call, x1, x2. Let me call that z. Fair enough? Just pick a new variable name.
Sure.
So that means this looks like z dot is equal to az plus, we'll call this b times u. Well, using that same naming convention, this last one down here looks like y is equal to some other, I've used ab, we now call it c times z again, plus next letter is d times u. So you will often see those letters are the common ones. If you take a look at MATLAB or Scilab or whatever else, when they have you describe a state space system, they ask you for the matrices A, B, C, D. Those are the A, B, C, D. That is exactly the, everybody uses, those are the standard letters. So those are the ones you'll go. This is the most common convention. This is the one that's standardly used in a lot of things. There is a slightly lesser used convention, just as a side note, that describes this in the sense of A is recalled to F, and B is called G, and C is called H, and there is no D. Does not exist. Okay? But remember, all that's saying is your control goes directly to the output. So you can easily cancel that out. So that's what they do. They just say ignore that, it's unimportant. Right? That's a straight feed forward system. It really doesn't do anything, it just biases your solution. So whatever you prove for it without that, you know, as long as your U itself does not go unstable, in which case you're screwed anyway. You know, why did you pick that?
Right.
As long as it itself is a bounded, it's going to have a bounded effect on the output because it never feeds back. It's just like adding a bias. So for this convention, if you use the FGH convention, you just say, you know, remove the bias and be done with this. And whatever you then prove for the reduced system will work. This one I like because it's A, most general, and it's the one you will standardly see in almost all the software packages. But if they ask you for them, that's them. And we kind of walk through an example of how to get them. If you notice, it was a lot quicker to go through. Now the question is, does it have the properties we want from it? Like for instance, we showed there's some important stuff in here. And we could actually take this S plus A2, and I could divide through, so this is the only part of the denominator. I could do that if I wanted, right? And I would have a simple little feedback system that goes on. The 1 over S plus A2 that would be up on top, some of them would not be affected by it. For instance, this one that uses B3 as it goes on. Right, so if you notice the ones that involve B3 should be fairly, you know, overall good on those as it go. Well, actually B3 won't be, whichever is the one that feeds at the end will go on. But what they'll do is each of these has a weight on them of whose components are they considering. They consider anybody who's downstream of them. So the S plus A2 would not be affected by any of the ones that are just picking up from the initial one, whatever state I call that, X3 or whatever. This is going on. Now, the reason why that becomes kind of interesting to us is it'll turn out that this top is completely determinable by just multiplying through on that one also. Right? When you multiply through the final answer for it, it will actually give you exactly the same thing. But most important to me, first off, is to show that these, which I contend to you are the most interesting ones, because that's, like I said, I can clear that one out. These ones, I need to show that they exist over here. So imagine for a sec that I turn the control off. I just said U equals 0. Right? That's what we call the homogeneous system. Remember I said if you don't put an input to it, that's the homogeneous, that's kind of how does the system work on its own.
Right.
So if I do that, those terms go away. And what I'm really left with is this is kind of the interesting part of what's going on. Z dot equals AZ. Fair?
Okay.
So this is just, I've set U equals 0. And just as a note, that's called the homogeneous solution. Okay, so I take the homogeneous solution. When you have U equals something else, it's called the particular. Now, we take this one, let's take its Laplace transform. So when I take the Laplace transform, I get S times Z equals A Z. Right? And what you end up with, take A to the other side, I have S I minus A times Z has to equal 0. At this point, people ought to recognize this if you've done any matrix theory at all.
Right.
That's an eigenvalue eigenvector equation. S is your eigenvalue, Z is your eigenvector. It's usually written with lambda for your eigenvalue and x for your eigenvector, but the equation for eigenvalues and eigenvectors is this. Right? So if you just replace the eigenvalue by S and you replace the eigenvector by Z, our state, it's the same thing. So I got an eigenvalue eigenvector system. But now that's for my variable S. And remember, what I'm trying to do is find out when Z is equal to something. So if I now took this same system and considered a forced system, it would look something like Si minus A times Z has to equal something that's forced onto it. Whatever the forcing equation is that you stick in there. Which means Z has to look like Si minus A inverse times F. Therefore, the question is, when does that go to 0? Because when Si minus A goes to 0, inverting it is like dividing by 0. Zero inverse equals 1 over 0.
Right.
Right? So now the question is, when does Si minus A go to 0? Because that is the poles of the system, by definition. It's exactly how we got them before. Now we're just getting into matrix form. It's absolutely no different. So that means all the work you did before, once you found A, can just be written as Si minus A. If you find what are the poles of that, you found the whole thing. Well, that's where the poles are, where the system goes to 0 at those points. That's at the eigenvalues. Well, how do you find the eigenvalues? Well, you take the determinant of that. Fair?
Yeah.
So let's take, this is the determinant of A. But we know what our A is in this particular case. Our particular A in this case is 0, 1, I think it's minus A1 minus A2. Is that how I... What? So I've got to take Si minus that. But that means Si minus that, I take S, I negate the A's, I get that. That's Si minus A.
Yeah.
I negated all the terms of A, put S on the main diagonal. Because S times I is just S's on the main diagonal. We agree. It's just a determinant of a 2 by 2. It's this times this minus that times that. So I get S times S plus A2 minus a minus 1 times A1. And we want to find out when that's equal to 0. But that's S squared plus A2S plus A1. When does that equal 0? So the eigenvalues, that's called the characteristic equation. So the characteristic equation of your matrix, which is what gives you your eigenvalues, gives you the poles. It's identical. Therefore, the eigenvalues are the poles. They satisfy the same equation. That's the big thing I wanted you to see. If you see that, you've got the big lump of this. Right? Which means everything you had to do with stability was centered around finding those. But remember, this was ugly as hell, right? And probably error prone. How tough was it to write that?
Not that bad.
It wasn't very hard at all, was it? So the reason why we're going to develop new math is because we are lazy and don't want to make mistakes. Okay?
Seems to be.
That's really what it comes down to. Because if I can do the same exact thing simpler, right?
Why would I do it harder? I mean, don't take it as any more profound than that. We looked at two different things and we said, classical control is neat. It gives me intuition, I can draw graphs, all this kinds of other stuff. But as the systems get bigger and bigger, it gets uglier and uglier. When I go to state space, it's really, really easy to write the equations. Since it's really easy to write the equations, why would I do it any other way? I mean, that's it, right there in a nutshell. And it gives me the same answer. It's 10 times easier over there. It make sense?
Yeah.
And everything you did before, we still have. Right? If you really wanted to, I could do the Bode plots of these things. I could do root locus. I could do whatever you felt like. Right? Root locus, I just get the characteristic equations. That's going to give me the poles. I can still plot the poles of the system. You want me to take a look at the zeros of the system? Remember, that's just if you multiply through by the y, include the b and the y, and multiply the whole thing through. As a matter of fact, if you wanted to, we could rewrite this equation right up here, which describes the whole thing in general. I could put that as a Bode plot. I could put that as a root locus. I could put it even as a block diagram if I would like. So how about we just put it as a block diagram? If I put it in a block diagram form, it's got to work for anything, right? So that's the next thing I'm going to do, is just show that I can take this form right here. I've shown how I can get this form from a block diagram. If I can show you how to put this into a block diagram, you could always undo it if you wanted to, very simply. Because block diagram algebra, while maybe a little bit tedious, at least is understandable. Sounds good?
Yeah.
Is it okay if I erase some of this stuff?
Yeah.
I'll be able to do it at least in this space. Let me try red. This will either make it a lot clearer to read or a lot worse. So our equation that we're trying to do is for z dot equals az, right, plus bu, and y is equal to cz plus du. Where these are now vectors. It's just a whole bunch of lines in parallel. So imagine for a sec, I've got z dot. But I also need to have z. How do I go from z dot to z? Integrate. We agree?
Mm-hmm.
So that's just a simple thing. I see I've got a z dot and a z. I want to know how to go between them. Integration goes between them. That's just by definition. How do I get z dot? Well, z dot is an equation by the sum of two things. So I'm going to need a summer.
Right.
And the two things that I need are a times z, but z's over here. Huh? And I need b times u. So I need my u coming in. I scale it by a b, and I stick it in. So far, so good?
Mm-hmm.
So now I've got the top equation described. Now I need my output. My output, since I'm flowing this way at the moment, has to look something like this. And my output y is c times z. Well, that means I need a c here. I have to add something else to it. And the other thing I have to add is d times u. There you go. It's a pretty nice looking one too. So let's reduce this. But I can simplify this, can't I?
Yeah.
So I just took those equations, I directly wrote what its block diagram must look like. I've got a feedback loop. Notice now it's not negative feedback.
Right.
But if it made you happy and you want negative feedback, I could always multiply by 1. If I put a minus here and a minus there, the net effect is multiplying by 1, isn't it?
Yeah.
Now it's in the form you're used to seeing. So this middle part right here, we've already shown is SI minus A. The reason why I know that's the case is, if you think about what's going on here, this is whatever's on top, 1 over S, over 1 plus, I've got my minus A 1 over S, but this one has to in particular be I now because it's a matrix. But since it's a matrix, I can't really write division. So now I have to write it kind of this way. It's the only way I can really handle matrix division. I have to say it's inverse. Right? So this is the equivalent of what we had before, right? But if I took this 1 over S out here, right, that's the same as I can multiply inside and outside by S. Because this is a 1 over. That means I get an SI, and it gets rid of this, and S times 1 over S goes away. So I get SI plus or minus A, which is SA minus A inverse. Isn't that what we said was what gave us our poles?
Yeah.
And look, we amazingly got the poles dropping right out of the equation. Again, so it's a second confirmation of exactly what we found the other way. Right? It doesn't matter which way you do it, you find the same things.
Right.
So far, so good?
Like, Z times 1 then? Or Z is 1 in that case? Or?
Well, that's technically, Z is the output of this, assuming you gave it the input that was coming in here. This is the block that replaces that.
Oh, okay. Yes.
That comes out and goes into C.
Yes.
And I now have a block B that comes in. I've got you this is just, all we did is we took this whole thing and replaced it by its equivalent block.
Right.
Good? All right. So now all I have to do is take these and the B and the C and multiply them. This is where it's matrices. Order matters. Okay, and this is why I made the comment early on, everybody draws it left to right. But left to right is the wrong damn way to write it. Okay? And the reason is, what would you do when you multiplied these?
B times
Your
C.
natural thing would be to say B times this times C, right?
Right.
But think of what that means. What you would get is that your Y is equal to B times SI minus A inverse times C. Now, what's the dimension of B? Just for our initial example we gave. What was B's dimension? It's 2 by 1, right?
Yes.
So, this is a 2 by 1. A is a 2 by 2 matrix. Add SI to it, it's still a 2 by 2 matrix. Invert it, it's still a 2 by 2 matrix. So this is a 2 by 2, and C is a 1 by 2. In order for matrices to be compatible, the inner dimensions must agree. Do they?
No.
They do not. This is why I say it's the backwards way to write it. What you have to remember is C is where you get your output from, so it had better be on the left-hand side.
Okay.
Because when we multiply going right to left. The input comes in on the right. Right? You want something that looks like your output is equal to some ugly mess times U. I have the U coming in on the left here, but in my equation I have U coming in on the right. Here I have Y on the left, here I have Y on the right. And amazingly, if you take this as the direction, you discover you're backwards when you write it the opposite direction. This is why I make the comment to you, it actually would make a hell of a lot more sense if we had written it the other way. This is the mathematical equivalent of when Ben Franklin picked protons moving, not electrons. Okay? It's the same damn problem. I mean, technically, you're fine as long as you remember that it's just going the opposite direction. It's the same thing here, exactly the same. As long as you remember it's going the opposite direction, you'll be fine. The second you forget, it doesn't. So you have to just remember that U goes into the B, so U goes into B, and then the output of that goes into SI minus A inverse. Goes into SI minus A inverse. That goes into C. That goes into C. And then we get this, at the end of that whole thing, we get a plus D.
Right.
Backwards. Now, let me just note something to you. If you had written this in reverse order, which is the way I believe you should have done it, or anybody should have done it, but no book in the world does. If you had written this so that Y was over here, and coming in was C, and then you have your SI minus A inverse B, there's U coming in, and there's your D. If you wrote it this way, watch what happens. Y is equal to C times SI minus A inverse times B plus D, multiply that whole stupid thing by U.
Right, and
And you just write the equation down, I mean, directly from the graph. You don't have to do any funny substitutions, any twists, anything else, because you've removed the twist in the graph.
you're going to run into that problem anywhere, though, because we read and write left to right. And in this case, we're writing right to left and then reading left to right. And if you do it that way, you're going to be writing left to right and reading right to left.
No, if you
So-
think about when you draw a graph, there is no natural which way do the electrons flow.
In the graph, it would look fine.
When I draw the graph, it looks fine.
Yeah.
When you write your equation, it looks fine.
Yeah.
That's the only two things you do.
If you're writing your equation from that, though, then again, you're still kind of looking at it left to right and writing it right to left, which is what I'm saying that
No,
conflict of the two.
I am writing it straight down.
Right.
You're drawing the initial
But-
graph, you're writing.
You mean drawing this initial thing as it goes. But the
Yeah.
point is, when you're drawing a graph as you're drawing, it doesn't matter. I could draw it up and down. When you're drawing something like if you're drawing a schematic, who says your schematic has to have inputs on the left and outputs on the right?
Doesn't. Convention. That's it.
Yeah, it's purely conventional. Neither one is more intelligible to you.
Right.
That's my convention. This is your schematic. From the block diagram, you can go to a schematic. So my assertion to you is you've learned it the other way
Right.
because people told you that's the way to write it. But then that way makes it hard to write equations from it. If you had just learned it the other way around, then both of them would work naturally. As a matter of fact, I find it easier to draw the graphs this way when it's going on, because I can just say the outputs. What comes into the outputs? Well, C and D go into the outputs. Right? Why C and D?
Yeah, it reads much more
You
like
know.
an equation than. Yeah.
And then as you read through each of them, then I have to take, next thing is I go to the next one, oh, it's the A term and then the B term. The A term and then the B term. I assert to you, it reads easier no matter which way you go. Because I'm putting them all in the same direction. If you want the graph to go the other way, then you ought to write the other stuff all backwards, but you'd have to redevelop all math. Because all your multiplications are going to be different and everything else. So, I mean, you could, but I think it's just a hell of a lot more confusing. Do you have to do it this way? No. I just assert to you it becomes easier. It's direct from here to there, and then direct from there to there. Whereas when I go from here to here, notice I had to write it backwards.
Yeah.
I mean, I see the U and I have to go to the B, right? So when I look at this equation, I have to take this equation and I read it from the right and write it on the left.
Yeah.
So I have to read this one right to left and this one left to right. Then when I write it again, I have to again do that same flip.
Right, and if you're in any regular scripting or programming language, whatever, you know, most things are written.
Almost everything is written this way in
Yeah.
programming languages.
So it makes sense to read it that way.
Yeah. So that's how you write your math. That's how you write your programs. I submit the way we draw our block diagrams are inconsistent with the way in which you do the two other things. And since it is arbitrary, it would make more sense to do the other.
To switch
Now that being said, the only person I know who does it this way in any consistent manner is the person who taught it to me. Okay, which was one of my committee members when I was doing my PhD, Roy Smith at Santa Barbara. But he's right, it's easier. So if you ever have to do it, this in any decent amount. If you're doing one or two off, just do it the way everybody else does it, right? Because you just read it up in a book and you're done. If you ever have to do a ton of these, doing it the opposite direction makes your life tremendously simpler. So if you plan on, and I know several people have said they were interested in doing controls for graduate study, this becomes much easier to learn if you decide to go on in this. Right, it'll just simplify your life. If you're not planning on going on, by all means, proceed as follows. Okay, it'll work lovely. Everybody else's forms look like that, and you're done. Good?
At that lower level, they may not like you drawing it that way because they're not used to seeing it any other way.
They're
but
not,
anyway.
yeah. And so, you know, they will have a huge conniption when you do it because there's a lot of people who are not even aware that writing it in the opposite direction works nicer.
Cool.
So that's kind of my just little aside if you're interested in going on in this. All right, so let's take this and simplify the answer now. Right? Or, oh yeah, we already did. Okay. So when we write it this way, you now have your answer. This was, remember our final solution, and this one is 1 by 2, this is 2 by 2, this is 2 by 1, and that's 1 by 1. And if you notice, inner dimensions agree, and this is a 1 by 1 plus a 1 by 1.
Good.
So you're golden. That equation is consistent. So now you actually have, this is your solution. I mean, that is the final solution. In time domain, I mean, assuming you take that inverse Laplace transform. So it's nice and simple as it goes. But what happens now is, since this is SI minus A, remember we can rewrite those expressions as if it was just on the main diagonal as each of the eigenvalues as it goes. So it makes a nice way to rewrite the A matrix. Has everybody had some amount of eigenvalue, eigenvector at some point? Because I'm not sure when I draw that statement out, did I just say
Everybody
something that's like,
sees it that way, right?
okay, just stare at him nicely and move on, right? Yeah, it's a couple of people say no. I'm assuming there's actually a lot of people who just don't want to say they don't know. Okay, so I'm going to do a slide aside and show you why I'm making the statement that I'm making. There's some neat properties about
Yay.
yeah, red erase is much nicer. Okay.
Sorry, blue.
Yeah.
Glad we found out at the very end of the quarter.
Yeah, that's awesome. Okay, so we've got our expression, let's say, we've been talking about A and we're saying what were its eigenvalues and eigenvectors. And I mentioned the fact that there is this equation, lambda I, right, minus A times X equals 0. I said that's the eigenvalue, eigenvector equation. Lambda is called eigenvalues, X is called eigenvectors. Let me just rewrite this slightly. If I take this and multiply through, I get lambda times I times X minus AX equals 0. And I times X is just X. That's what it means to be the identity. Okay? I times anything just returns it. It's the equivalent of 1 in matrix land. Okay? All right. So now I've got this. Now I can take the AX to the other side. That means lambda X has to equal AX. Now, I submit to you there's something kind of cool about what this is. Think about how big. Lambda is a scalar. Right? So it's a 1 by 1. X is a vector. It's, n theoretically, if there's n states, it's n by 1. This is a 1 by 1 times an n by 1. What's the complexity of doing that multiplication?
Big O of that.
It's big O of n. You have to take this scalar and multiply it by every one of those elements. So this is big O of n. Right? It's equal to, well, A is an n by n, and X is an n by 1. Compatible again, lovely, we're happy with that. But now think about it, an n by n by an n times an n by 1. Huh?
By 1.
What does that look like?
N by 1.
N squared.
Oh, big O.
Yeah, big O wise. Right?
Yeah. N squared.
N squared.
Yeah. Okay, I almost went. I was like, no.
Right?
Yes.
Those who are thinking n cubed, you're thinking n by n matrix times an n by n matrix.
Yeah.
Matrix multiplies n cubed. Matrix vector is n squared. Right? And either vector or scalar vector is n. Each time you go down a size, it goes down a size. Right? So it's kind of nice to remember as it goes on. But think about that. What that means is, if I'm trying to take some particular pattern of my states and figure out how it's going to affect the next instant of what's going on, I could either do an n squared algorithm to get it, or an n algorithm. Which would you rather do, big O n squared or big O n? That's kind of a neat thing if you think about it when it goes on. But it's got a lot more implications than that as it goes. But this one right off the bat, that's kind of a nice thing if I can reduce your complexity in some sense. Now what this is telling you is there are some vectors that are out there that when you apply them to the matrix, it just gives you a scaled version of it back. So imagine like some two-dimensional space where you just have two components, x1 and x2, as it's going on. And this particular vector x is, say, pointing out this way. Whatever my eigenvector is, it's some combination of x1 and x2. So that one, when I multiply it by a, it points in the same direction, it's just scaled. Maybe a little bigger, maybe a little smaller. But that's what you're looking at. It's scaled. That's all it does. Right? It doesn't point in a different direction or anything else. That's what that equation is telling you. And therefore, since it's pointing in the same direction, I don't have to recalculate the direction, I just have to calculate the size. And this is just saying you can calculate scale the size. This is your scaling factor as it goes on. Now remember, when we were looking at our poles and we did our root locus, we were looking at where did those poles occur. And remember, the closer it got this direction, it started going slower and slower, right? And the further it went this way, it got faster and faster. That's telling you something about how it's scaling in time, isn't it? How your response scales in time. You go, get something that shoots off in complex conjugate pairs, and they oscillate. So it's giving you some information about how this thing is behaving. Well, we can get eigenvalues that come in complex conjugate pairs too. So, eigenvalues and eigenvectors give us some nice things from a computational standpoint as it goes on. So that's kind of a nice feature when we're handling them. Now, when we're going through and doing a lot of these ones and taking a look at inverses, there's another nice thing that happens because of this. If I take each of these, right, there's a whole bunch of these different eigenvector, eigenvalue combos. So let me go back to here. I'm going to start, now this is kind of overloading terms a little bit. I had been calling x1 to be a particular component. So let me actually just put in parentheses. If I put in parentheses 1 down here, I'm talking about the first eigenvector.
Oh.
And its associated first eigenvalue. Normally we don't put the parentheses, but I'm just trying to give you something so you can distinguish them. Normally we call the components x1, and we call the eigenvectors x1. And you have to know whether I mean an individual scalar or do I mean a vector. And it's completely by context, and you just have to recognize it. Okay, and there's really nothing other than you just have to understand how it's being used to figure out. And it's the same way when you overload a function in C++, right? By what you pass in, it looks at the size of it and determines what is the correct one to run. Well, same thing here. You can look at the size of them and determine, did I mean the component or did I mean the eigenvector?
Size or type.
What's that?
Size or type in C++.
Yeah, size, type, same idea, right? I mean, because the different size things are going to affect type. So,
Sneaky.
yeah, isn't it? So it really is the same idea. So we normally just leave that off, but when you're first seeing it, it can get confusing. So I'll put parentheses, but don't make that too long of a correction. That's kind of my side note on here. That means there's also, in this case we had a 2 by 2, that meant there was 2 of these eigenvector eigenvalue pairs.
Right.
And as long as my eigenvalues are distinct as they're going on, they're guaranteed to both exist. And everything's nice and pretty. So let's assume at the moment we have nice distinct pairs like this. What it's telling you is that as long as lambda 1 and lambda 2 are not equal to each other, and if they are equal to each other, I can still pull out 2 separate ones of these. That's what we mean by it's not a degenerate matrix.
I understand a singular could be 1.
Yes, but it's in particular, the most precise thing is to say it's degenerate. But if I say degenerate, it's again, not going to mean a lot to people. So I'm, trying to put back in the terms you're used to as we're going through, which is just saying, in order for it to be degenerate, these two have to be equal to each other, and you can't find 2. Right. Therefore, in order to get the second one, you've got to do this thing called Jordan forms. I'm not going to worry about that at the moment. Right. These are 2 nice little separate equations, which means I can write them as a matrix. Lambda 1, x1, just one in parentheses, lambda 2, x2. Let's just do that on the left-hand side. Well, that has to be A multiplies both of them. It multiplies x1 to give me that one, and it multiplies x2 to give me that one. First column here times A gives me that. Second column times this gives me second column. So it's just a compact way of writing these 2.
Yeah.
So far, so good? All right. Now, if you think about what's going on here, then that means lambda 1 multiplies x, so lambda 1 has to be able to pull out. All right? Lambda 2 multiplies here, so it has to only multiply the second one. That's going to look at lambda 1. Now consider this. All right? When we're going on, what I'll get is lambda 1 times x1 and 0x2, that's the first component. Second one is no x1s and lambda 2x2, which is what you have up here. So I submit to you this is that.
Yep.
That's just multiplied and showed it. Okay? So all I did is just multiply those 2. So this is equal to that. And that just came from right here. Just wrote it in. So that has to be equal to A times x1, x2. Fair?
Mm-hmm.
But now I've got this on both sides. Let me give it a new name, capital X. It's the vector of, or the matrix of all eigenvectors. I call this a diagonal matrix of the eigenvalues. I'm going to call that capital lambda. Equals A capital X. Okay? So far, so good? Here's where it gets kind of cool. Imagine this is an equation. So I can take, let's say I want to know what A is equal to. Well, what if I multiply on the right by x inverse? X times x inverse
I or
is identity, which then just gives you A. Right? Now, here's the fun part about this. This is giving me an expression to calculate A. But it also actually simplifies a whole bunch of my matrix operations, because we can use a Taylor series expansion to write functions of A. So this is, I want to now be able to use this, and I want to show you why this is so darn cool. Okay? So consider the following. Okay, if I erase this side. This is why we care about that. So consider some function of matrix A. All right? So let's say it's like some function of matrix A is equal to, I don't care. Let's even, we'll pick one that actually matters to us. Technically, we'll say this is of A and T. All right? And let's say it's e to the AT. Now, why do I care about e to the AT? What's the derivative of e to the AT? A, e to the AT. Right? Now this is an exponent of a matrix. Sounds kind of ugly, right? But notice that's what that's equal. That's the derivative. So imagine that this, right, times some initial condition. Let's say I call this some x. Well, its derivative, that's just a constant. The derivative of x would just be this times that initial condition. Right?
Mhm.
But this is x. You know why you care about e to the AT? Because we can write a whole bunch of stuff in this form, can't we? X dot equals AX. Z dot equals AZ. It's the solution to our whole thing. This is actually what you are looking for. That is the solution of everything you do. Okay? This is why we did Euler's before, right? Because it's, if these were little individual ones, you'd get like e to the minus 2t, right? Decaying exponential. But remember, I told you if it's a complex conjugate pair that's in here, then what you end up getting is something that uses that as an envelope and it comes in as a sign. But remember, Euler's tells you something about e to some complex, right? Right? Euler's tells me that's cosines and sines.
Mhm.
If I multiply that by some damped exponential minus AT, this gives you the size, the outside envelope. That gives you sines and cosines, which is the oscillation inside. But that is just equal to I minus AT plus some phi I. And away you go. All right? So if your eigenvalues end up being complex conjugates, it oscillates. If they end up being purely real, it just decays. We already showed that in root locus. Same thing happens here. It's nothing new. But this ends up being, when you take those inverses, it's always something that looks like e to the AT or sines and cosines, which we showed sines and cosines are exponentials. So this is kind of nice. As long as it's a linear system, that is your solution. Okay? So that's kind of nice as it goes through. Now we have to be able to calculate that bad boy. Right? What do you even mean by that as it goes on? I'm thinking an exponent of a matrix.
Right.
And those, it might be a matrix that might even have complex values inside of it. Right? Well, we talked about how to deal with complex values. That's Euler's, but I mean, how do I deal with the matrix? Well, the way I deal with the matrix is I would like to take the Taylor series expansion of this. Because the Taylor series expansion expands at about some point, and I just get polynomials.
Right. Does MATLAB do that for you if you were to try and plug that in?
No, there's
approximate
actually
that
a
way?
ton of ways to calculate this, and almost all of them are bad. Okay? So, solving this equation actually becomes a very important thing, and that's what 535 sets up. It goes through, I don't necessarily always tell you at every time this is underlying what's going on there, but it turns out that we're talking in there when we develop those methods, intelligent ways of solving this. Because if you think about it for a sec, when you've got the SI minus A inverse, which is what generates this, right, I've got something, whatever you want to call it, P times the SI minus A equals some B as it goes. That's the same as saying P is equal to SI minus A inverse times B. All right, so if I find P, I found this part of the expression that's going on. But this, right? This is just some matrix. P is something I want to know.
Yeah.
Right? So this is in our standard form. A matrix times an unknown equals a known.
Right.
Right? So we did this in the form AX equals B.
Yeah.
Right? So when you were solving that, it ends up you're finding out how to do this in general, which now means you can start intelligently solving it. But it turns out it's very ill-conditioned if you don't do it that way. So remember, this Taylor series is great to prove things and crappy to implement. Okay? So it'll convince you why it's true, but please do not ever do this. It will fail miserably on you. Okay? So let's say that's what it is. Well, when I take a look at this, it's just f of a at t0. You take it to whatever your initial point is. Wherever you want to go, you just take the point you're resolving around, and then you keep taking derivatives of this, plus the derivative of that function, evaluated at t0, times, and now we need our t minus t0. Right? This is just the shift, t minus t0. How far am I away from that point? Times the slope. Right? Because f dot is the slope. So that's the offset plus the slope times the function. It's just a line.
Right.
Plus second derivative, that's the curvature at the point you're interested in. But that means you have to take how far are you from that point squared over 2 plus dot dot dot. Right? Fair enough? So you get an expression that looks like that. Okay. Let's consider a really easy spot where t0 is 0. Your starting condition is just 0. It makes life just a little bit nicer for us as we go through. It doesn't have to be, but we'll consider the case t0 equals 0. So, and f of at is this, so f at a comma 0 is e to the a times 0.
Which is 1. Or, well, no. There's
Right.
a matrix there.
It's the matrix equivalent of 1.
Yeah.
What's the matrix equivalent of 1?
I.
I. This first term is just the identity matrix. All right? Now, plus I've got this f dot, so I need the derivative of this. Well, the derivative of this is a e to the at,
So you
and I'm going to evaluate at t equals 0.
get A.
Right? So that makes this is just the identity, so that's a times t minus t0. The second derivative, I have to take the derivative of this before I stick in t equals 0. Huh? So I get the derivative of this one again, which means it's a times the derivative of what's inside, which is a e to the at. And then this becomes the identity when you stick t equals 0 in. A times a is
A squared.
a squared. t0 was 0, so I just have t squared over 2. I continue the pattern as it goes. Notice what ends up being nice? No longer do I have an exponent. Now I got a polynomial expression. Right? That's not too bad. Actually, it's even nicer because I said t0 equals 0. So that should just be at. Now, the only problem with this is I have to like square a's and stuff. That's kind of horribly ugly, isn't it? Right? I mean, because remember, that's a matrix times itself. That's an n cubed operation. I don't want to do an n cubed operation. That's like work. Okay? And it's going to be slow.
Yeah, it is.
So let's take a look. We have a way to substitute for A. A is equal to this. You might say that looks like more work, but it's not. That's much less work. See, what looks like work at first to a human being often ends up not being.
It's so true.
Okay? So I know that this A is this big X lambda big X inverse, right, times t. A squared, I'll deal with the I in a second, is X lambda X inverse X lambda X inverse times this t squared over 2.
Ooh.
Now, notice what happens in the middle here.
Yeah.
X inverse times X just goes away. But now notice, this is X times X inverse. X inverse on the outside edges. What do you think is going to happen when I deal with A cubed?
Same thing.
Right? You're going to end up with X times lambda times X inverse. X lambda X inverse, the middle ones kill. X lambda X inverse, the middle ones die again. And you still have X inverse on the edge.
Yes.
So everything has X
Lambda
inverse.
times the power.
So I need to replace identity by another form of 1. But we know X inverse is the same as identity. But now it's got the same form everybody else does.
Right. So same size, you can add them.
X is all on the same side, factor X out. There's an identity in the middle there,
A step further.
plus lambda times t, plus lambda squared, t squared over 2, plus, keep going, and an X inverse on the outside. But these are diagonal matrices, which means it's n independent, i.e. parallel,
Right.
scalar operations. You really could not ask for a nicer thing that does that.
Do you ever see those when you're doing your proton stuff? Because you do that on your GPU, right? Your calculations, so you could parallelize that very easily in your work?
So anything that ends up being like that ends up giving you things that scales quite nicely. So in some of these things you end up finding out that when you end up going out to here, this one, the diagonals multiply the columns of X, and in this one it multiplies the rows of X inverse. And so you'll often see these cases where you go between multiplying row and column form of the multiplies, and you just have to synchronize between the two. And that's where your biggest slowdown. The second I say synchronize, right? That's where the slowdown happens, is when you actually have to multiply these two. But it's very quick inside, which reduces a lot of the complexity, huge speed ups. And then in the end, you still have to kind of get the correct distribution, but I only have to do that once now.
Right.
So yeah, it does give you a lot of speed up, and that's why we know these things have to give us speed up, for exactly those reasons.
Awesome.
So if you look at this, it allows me to diagonalize equations, which means parallelize your code. So realize, by making that one observation that it's equal to eigenvalues, and then kind of playing around with the equations a bit, we were able to actually start from a block diagram and get to the point where we could talk about how you would parallelize code to get speed up for it. That's actually kind of cool if you think about it. In a very short period of time, and we just said this for anything that fits that linear assumption, anything that matches that model up there. Okay? If it's nonlinear, z enters as a square or something like that, then things you now have to deal with nonlinear equations as it goes. But as long as it's linear like that, I've got all kinds of tricks up my sleeve for it. And we can do things parallel, we can speed it up like crazy, all kinds of great, beautiful things. And everything that you did before still applies, the intuition, as long as we've showed the eigenvalues are the same as the poles. As long as the eigenvalues have negative real parts, it's got to be stable. So the whole game now is, for any control you do, is to check to see, does the net result after your control has been applied, do the eigenvalues of that system end up having negative real parts? If they do, it's stable, you're done. Okay? And now you can pick any control you want. You're not limited to just the ones that they want to give you according to a form. You can pick anything. So this is actually even more general. So it's slightly easier to develop. It is easier to manipulate. It naturally shows you how you program it in some reasonable fashion if you think about it, right? And it also gives you the added bonus of, you know, on top of simplicity and everything else, it's elegant to write. There's, besides understanding things, there's really not a lot of reason to go into classic controls. Right? You need to understand it, otherwise it doesn't make sense why I make those assertions. And you won't see what's happening with it. It still makes sense on a single line to do a bode plot, but in a grand scheme of things, it's kind of primitive.
How long do they do it that way before they found the better way?
Actually, believe it or not, the matrix ways of solving these in general for nonlinear stuff came out in the 1800s.
It just wasn't applied. So
Yeah, a Russian mathematician named Lyapunov actually came with one of the most general things what are called Lyapunov functions that go on, and it's basically an energy thing. And it just says, his basic theory says, if you watch the trajectories of your system, and you give it some input and you take a look at the outputs, if along every possible output line, whatever energy function you picked is always decreasing, it's stable. And there's a very nice mathematical formulation of that, and you can pick any old energy function you want. You're not stuck with actual energy functions. But anything that looks like an energy function will actually, you know, still work. So, and he showed that in the 1800s. But it took a while for people to understand that this was necessarily the easier way, because most people went, oh my God, that's nonlinear, right? And even a lot of people today go, oh my God, that's nonlinear.
Right.
And so they run away from it. The neat thing about this is this extends into nonlinear. The classic stuff, you know, it's really hard to handle that stuff in any.
Isn't a lot of it
fashion.
like approximated though if you're going
Yeah.
okay.
And that's what usually happens. And there's, you know, you either have to handle it directly through Lyapunov techniques, or you have to go into what's called robust, which means you pick a nominal model and then you force it to work for everything in a region. Right? So you linearize and then say it's got to work for a bunch.
Okay.
So you just don't pick an unlucky one nearby something bad that causes you to blow up. You got to make sure it's safe if you're going to linearize. That's what robust stuff does. I've gone slightly over, but part of it was if I stopped at any one point, I would be afraid that I would not be able to pick it up in an intelligent fashion next time. My real hope for this one is we showed from taking a nice little simple, you know, block diagram thing, we showed we could get the damn ugly looking expression that showed us where ones. We showed we could get a very easy one. And then we said, hey, look, we made the correlation between the eigenvalues and the poles. And we said, furthermore, the eigenvalues allow us to talk in some sense about ways I can solve things, and so that, you know, we could actually say what the answer of the whole thing looks like.
Right.
You know, and we could develop a way that shows it's got to have some nice form, even though I said don't actually implement it this way. Right? There are better ways of doing it, but it shows that the system is diagonalizable, and therefore we would get something of that form. So that kind of gives you a first introduction of where it goes. So we can go from those to these, and we see, oh, why do we like it? It's elegant. It allows us to handle big, complicated systems simply. Right? That's what elegance is. So next time, my hope is we'll talk a little bit about how do we get into writing up a control for these. And what does that actually mean? So we'll take a look at what, this is kind of an open loop. Right? Because I did everything without the control. I said let the control u equals 0. Closed loop, I have to set in. We'll just pick a way to get the control, and we'll feed it back in and see what happens. Then we'll talk about different ways we can how do we select a good control out of all possible candidates. Sound good?
Yep.
All right. So that's it for the lecture, and we'll get on to lab. And thank you very much.